if you set up the similarity ratios and one of them is off, like let's say that this was a 32, and then this doesn't simplify to 1 to 3, it simplifies to 5 to 16. So if one of the ratios is not in the same, it's not the same, then they're not similar. In this case, they were all the same. They all simplified to 1/3. Oops. So that's the similarity ratio, 1 to 3. What would the scale factor be? What are we multiplying the first shape by to get the second shape? Addie. Scale factor is 3. So notice that's inverted from the side ratio. Okay. A lot of it, we've gotten that part. We've got scale factor and side ratio are inverted, but we still do things, we're doing everything backwards. The side ratio is in order of the shape. We got small number, small shape. Big number, big shape. Like it's in order. The scale factor is what is not quite in order. Scale factor is you take something from the first shape, like 10, times the scale factor, and that equals the side from the second shape. Okay, so the actual answer on this slide is 1 to 3. Okay. If two solids are similar, all of their side ratios are the same, then the ratio of their areas is a squared to b squared, which is the same as when we were doing flat shapes. If the rectangles were similar, then their ratios were the square, bless you, of the side ratios. Volume is very similar. It's the cube of the side ratios. If the ratio is 2 to 5, then the volume is going to be 2 cubed to 5 cubed. Okay, questions there? All right. All right, two solids are shown to have a similarity ratio of 2 to 3. Surface of their smaller solid is 120 square centimeters. What is the area of the larger solid? Okay, so we start with the ratio of the sides is 2 to 3. We are trying to find area. So we need to know the ratio of the areas. Ethan. Good. Square both of those items, 4 to 9. Once you have the ratio that you need, we can set up a proportion so that we can cross multiply. The 120 goes with the 4 because the 120 is with the smaller shape, and the 4 goes with the smaller shape. Okay. Somebody help me out. What's 120 times 9? But remember, it's 1080. Yep. And then we got to divide that by 4. 270. So the area of the missing shape is 270 centimeters squared. All right, questions? All right. So there's a misprint on this one. Two solids have a scale factor of 2 to 3, but the way that I put them on the slide, it went small to big. So the scale factor is actually going to be 3 to 2. So that means what something on the first shape times 3 halves is going to equal something on the second shape. The volume of the big one is 5,832 cubic inches. What is the volume of the small one? So that means we need ratio of volumes. Start with ratio of sides. If our scale factor is 3/2, what is the ratio of the sides? Addie? That'll be area, actually. Layton. 2/3. It's the same numbers that are in the scale factor, but it's in order of size. 2 goes with the little guy, 3 goes with the bigger guy. This might be like their radius. 2/3. Then if we did ratio of areas, which we don't actually need, what would the ratio of areas be? Ethan? 4/9, because you take your ratio of sides and you square them. But unnecessary. We really need the ratio of volumes. Ethan? 8/27. Yes, 8/27. You have to go back to the ratio of sides and cube both of those. Don't look at ratio of areas and like try to square it. It doesn't work. It's the cubed ratio of the sides. Once you have the correct ratio, set up a proportion. Small over big, small over big. And then we're going to solve. 8 times that 5,000 number is 46,656. And then we divide that by 27 and we get x equals 1,728 cubic inches. 1,728. There's a big number, but it makes sense with the picture. It's smaller than the orange one, and it should have been smaller than the orange one. Okay. Questions on this one? All right. All right, if two shapes have a side ratio of 5/8, what will the ratio of their areas be? Excellent. 25/64. What will the ratio of their volumes be? Yep, it is. It's 5 cubed and 8 cubed, Lily. Thank you. If I can write it correctly here. 5 cubed is 125. 8 cubed is 512. You don't have to try to simplify these. If your ratio of sides was in simplest form, then whatever you square and cube should be in simplest form also. Bonus question, what's the scale factor? Really? Yep, 8/5. Don't write that one as a ratio because it's a number that we're multiplying. You can write it as a fraction or a decimal. 8/5. Excellent. Okay. We have two similar solid shapes and all the sides have been doubled. By how many times will the area increase and how many times will the volume increase? So if it helps, you can put some numbers in here. Like we went from a cube that was all sides 3 to a cube that was all sides 6. Ethan? Bigger. Oh, you mean the side, sorry, side ratio. Yeah. Side ratio is going to be 1 to 2. And that works no matter which numbers you pick to put on there. Because you could do 4 and 8, you could do 5 and 10, you could do 8 and 16. But they all simplify to 1 to 2. So what does that make our area ratio? Cassie? 1 to 4. So when we doubled our sides, what happened to our area? More than doubled. More than that, it quadrupled. When we doubled our sides, it quadrupled our areas because we went from 1 to 2 to 1 to 4. So it increased by 4 times. I won't write 4x, 4 times. And if you can use the numbers here again, I just did the front of the box. The front of the little box was 9. The front of the big box was 36. That's an increase of multiplying by 4. Increased 4 times. How many times does the volume increase? Say again. More. Chelsea? It went up 8 times because our volume ratio is 1 to 8 because it's 2 cubed. So it increased 8 times. And you could check it. You could do the volume of the 3 by 3 by 3 cube, and the volume of the 6 by 6 by 6 cube, and it would multiply by 8. Okay. Now, 2s are always funky because, like, you go from 2 to 4, and there's lots of ways to get there. So what if I tripled the side lengths instead? So you guys don't erase anything, but I'm going to change it to tripling. So I had a 3 by 3, and now it's a 9 by 9. What happened to my areas? Kelsey? Yeah, it went up to 9. So I went from 1 on the blue to 3 on the purple when I did sides. I went from 1 on the blue to 9 on the purple when I did areas. And an example would be if I put the areas down, this would be a 9 and this would be 81. That's a multiple of 9 there. And if we do the volume, how many times do we increase by? Kelsey? 27 is correct because it's 3 cubed. So when you double or when you triple the sides, you square that and you get times 9 for the areas. When you double the sides, you square that, you got times 4. So I wanted to show you this one because it's not just timesing by 2, it's squaring. Okay, one more that I want to do that's not on here. Let's say you know that the area ratio was, I don't know, 16 to 49. And the question is, what is the volume ratio? Ethan. Excellent. He said square root it and cube it, which is exactly what we need to do. First, we need to go up to the ratio of the sides. So that would be 4 to 7. And then from there, you can go down 64. I don't know what 7 cubed is. 343. So you cannot go directly from area to volume. You have to go back to the sides and then down to whichever one you need. All right. Questions in the room or at home? Okay. You have a short homework assignment that goes with this. It's only 2 pages long. We'll have the quiz for this on Tuesday because that's all there is compound solids and similar volumes. And both of those are real close to the previous thing we did. So we just added like one more layer there. Share this tab instead. All right, so that's what the assignment looks like, Eddie. We have a whole nother unit. We have to do circles. So we got 4 weeks. Probably 3 quizzes left.